this lesson, I'm going to be modeling with quadratic equations. And then Steve's going to graph some quadratic equations, but instead of having those quadratic equations given in standard form, they're going to be given in vertex form, which you can also refer to as graphing form. Anne's going to be starting with some graphs and then write some quadratic equations, both using standard form and vertex form. So let's do some modeling. Let's find a quadratic equation that has solutions 0, 6, 112, and negative 1, 2. Remember the standard form of a quadratic equation, ax squared plus bx plus c equals y. Well, I have 3 solutions for a quadratic equation, and so I can actually come up with 3 equations. Thinking about that first solution, 0, 6, well, since y equals 6, when x equals 0, then using our standard form of a quadratic equation, we have a times 0 squared plus b times 0 plus c equals 6. And we can do the same thing with our other 2 solutions. Since y equals 12, when x equals 1, we have a times 1 squared plus b times 1 plus c equals 12. Working with that third ordered pair, since y equals 2, when x equals negative 1, we have a times the square of negative 1 plus b times negative 1 plus c equals 2. So we actually have 3 equations here, and we're trying to find the values of a, b, and c. Well, if we simplify this a little bit, we'll see that the first equation right away simplifies to c equals 6. So we know the value of c. The second equation is a plus b plus c equals 12. And the third equation is a minus b plus c equals 2. Well, since I know that c is equal to 6, I can substitute the value 6 in for c in those second and third equations to simplify things. So the second equation becomes a plus b plus 6 equals 12. And the third equation becomes a minus b plus 6 equals 2. Well, moving those constants over to the right-hand side, my first equation now becomes a plus b equals 6, and the second one, a minus b equals negative 4. Now I have a system of 2 equations with 2 unknowns. We actually talked about 3 different methods for solving linear systems of 2 equations and 2 unknowns. First, we did graphing to solve these systems. We also looked at elimination and substitution as methods to solve these systems. I think for this first example, I'm going to use the elimination method. And I'm choosing that because I see a plus b in the first equation and minus b in the second equation. So if I add the respective sides of the equations together, the variable b will be eliminated. So I have a plus b equals 6, and I have a minus b equals negative 4. Adding the respective sides together, I have 2a equals 2, which tells me that a equals 1. Well, when a equals 1, since a plus b equals 6 from that first equation, b would have to be 5. And we already knew c was 6. So we've got a is 1, b is 5, and c is 6. I need to check those. Well, let's think about the quadratic equation we'd be thinking about here. Standard form again. Y equals ax squared. So in this case, 1 times x squared is just x squared. Plus bx. B is 5, so plus 5x. Plus c, and c is 6. So the quadratic equation I'm coming up with is y equals x squared plus 5x plus 6. But I want to make sure that those 3 solutions actually satisfy this equation. So first, let's check if x equals 0. Well, if x is 0, then we want y to be 6, since we have the ordered pair 0, 6. So if x is 0, y is 0 squared plus 5 times 0 plus 6. Which is indeed 6, so that checks. What about if x is 1? Well, I'm hoping y is going to be 12 since I have the ordered pair 1, 12. Well, y would be 1 squared plus 5 times 1 plus 6. 1 plus 5 is 6, plus 6 more is 12. So that checks. Finally, what happens if x is negative 1? Well, I'm hoping y will be 2. Let's find out. Y is going to be the square of negative 1 plus 5 times negative 1 plus 6. That's 1 minus 5 plus 6. That's 7 minus 5, which is 2. That checks. So I can say that a quadratic equation that has solutions (0, 6, 1, 12, and negative 1, 2) is y equals x squared plus 5x plus 6. Well, let's graph this quadratic equation that we just found. Well, the first thing I'm going to think about is the horizontal intercepts. So I need to find out what happens when y is 0. So let's substitute 0 for y. I can factor that right-hand side as x plus 3 times the quantity x plus 2, which tells me x equals negative 3 or x equals negative 2. So the x-intercepts are negative 3, 0 and negative 2, 0. Well, what about the axis of symmetry in the vertex? Well, x is going to be the opposite of b over 2a. In this case, that's the opposite of 5 over 2 times 1. So that's negative 5 halves. So the axis of symmetry is x equals negative 5 halves. I also know the x-coordinate of the vertex is negative 5 halves. What about the y-coordinate? Well, if x is negative 5 halves, then y is the square of negative 5 halves plus 5 times negative 5 halves plus 6. That's 25 fourths minus 25 halves plus 6. Getting a common denominator, that's 25 fourths minus 50 fourths plus 24 fourths, which looks to be negative 1/4. So the vertex is negative 2.5, negative 1/4. Well, let's graph all of the points we know. We have the 3 solutions that were given, the 2 x-intercepts and the vertex. So there's 6 points, and then I can use symmetry, since I know the axis of symmetry is x equals negative 5 halves, to find 3 more points. So by symmetry, we also have these 3 points. And graphing the parabola that goes through these points, we had a parabola that looks something like this. Now let's find a quadratic equation that has solutions 0, 2, negative 1, 2, and negative 2, 0. Thinking about our quadratic equation in standard form again, ax squared plus bx plus c equals y, I can use those 3 solutions to come up with 3 equations. So my first solution, 0, 2, leads me to the equation a times 0 squared plus b times 0 plus c equals 2. My second ordered pair, negative 1, 2, gives me a times the square of negative 1 plus b times negative 1 plus c equals 2. That third ordered pair, negative 2, 0, leads to a times the square of negative 2 plus b times negative 2 plus c equals 0. So what happens when I simplify these 3 equations? Well, the first equation tells me the value of c again. C equals 2. Notice that's because we're given the vertical intercept of our parabola, 0, 2. The second equation is a minus b plus c equals 2. And the third equation simplifies to 4a minus 2b plus c equals 0. So again, I have the value of c. I can substitute 2 for c in the second and third equations to simplify this a bit. So a minus b plus 2 equals 2, and 4a minus 2b plus 2 equals 0. Now moving those constants to the right-hand sides of the equations, I have a minus b equals 2 minus 2 is 0, and I have 4a minus 2b equals 0 minus 2, which is negative 2. So I'm left again with a system of two equations with two unknowns. I need to solve for a and b. This time I think I'm going to use the substitution method. Look at that first equation, a minus b equals 0. Well, that tells me that a equals b if I add b to both sides of the equation. So I'm going to substitute b in place of a in that second equation. So substituting b for a in 4a minus 2b equals negative 2, this gives us 4b minus 2b equals negative 2. Simplifying, 2b equals negative 2. Dividing both sides of the equation by 2 gives me b equals negative 1. And since a equals b, that also tells me that a equals negative 1. We already knew the value of c was 2, so now we have a and b are both negative 1 and c is 2. So our quadratic equation would be y equals ax squared, that's negative 1 times x squared, so the opposite of x squared, plus bx, that's negative 1 times x, so minus x, plus c, which is 2. Now I need to check that the three solutions I was given actually do satisfy the equation I came up with. So starting by checking x equals 0, I want y to be 2 because I have the ordered pair 0, 2. So if x is 0, y is the opposite of 0 squared minus 0 plus 2, which is indeed 2. What about if x is negative 1? Then I want y to be 2 again because I have the ordered pair negative 1, 2. Y would be the opposite of the square of negative 1 minus negative 1 plus 2. So that's the opposite of positive 1 plus 1 plus 2, which is indeed 2. So that second ordered pair checks. What about the third one? If x equals negative 2, then I'm hoping y is 0. Well, y is going to be the opposite of the square of negative 2 minus negative 2 plus 2. That's the opposite of positive 4 plus 2 plus 2, which is indeed 0, so that one checks as well. So now I know a quadratic equation that passes through these 3 points. A quadratic equation that has solutions (0, 2), negative 1, 2, and negative 2, 0 is y equals the opposite of x squared minus x plus 2. Let's graph this quadratic equation that we just found. This time, I'm going to look at the points that I have, and I've noticed that I have 2 points that have a y-coordinate of 2. So I'm going to try to use symmetry and graph this a little bit differently than I graphed the last parabola. So let's plot these 3 points. Since I have these 2 points, 0, 2, and negative 1, 2 over here to the left, that both have the same y-coordinate, I know that the axis of symmetry is going to have to lie halfway between here. Well, the x-coordinates are negative 1 and 0, so the axis of symmetry is going to have to be x equals negative 1/2. Well, the vertex is going to have x-coordinate negative 1/2. And if we plug negative 1/2 in our formula for our quadratic equation, we'll find that the vertex is negative 1/2, 2 1/4. Now I know one of the x-intercepts is negative 2, 0. I can use symmetry to find that I should have another x-intercept 1.5 units to the right of the axis of symmetry. So I should have another x-intercept at 1, 0. So graphing the parabola that goes through these 5 points looks something like this. When a ball is kicked, it goes up into the air, reaches a maximum altitude, then comes back down. Assume, therefore, that a quadratic function is a reasonable model for this situation. Newton actually used calculus to show that this is true. When the ball was kicked, it was 4 feet above the ground. 1 second later, it was 28 feet above the ground. 2 seconds after it was kicked, it was 20 feet up. So let's find a quadratic equation to model this situation. Well, I'm going to start by defining my variables. I'm going to let d represent the distance in feet the ball was from the ground at time t. And I'm going to make that t seconds after it was kicked. Now I'm thinking about ordered pairs here. My ordered pairs are going to be in the form t, d. The distance depends on the time it was kicked. So I know when the ball was kicked, that's t equals 0, it was 4 feet above the ground. 1 second later, it was 28 feet above the ground. And 2 seconds later, it was 20 feet above the ground. So I've got 3 ordered pairs. So I want to find a quadratic equation that has solutions 0, 4, 128, and 220. So thinking about our standard form of a quadratic equation, I see that I have the wrong variables. I just defined variables t and d. I need to change those x's to t's and the y to a d. So this is the standard form of the quadratic equation I'll be working with my variables t and d. So looking at that first ordered pair, 0, 4, so t is 0 and d is 4, we'd have a times 0 squared plus b times 0 plus c equals 4. Then our ordered pair 128, a times 1 squared plus b times 1 plus c equals 28. And finally, the ordered pair 220, a times 2 squared plus b times 2 plus c equals 20. Simplifying those equations, again, the first equation gives me c equals 4. That was to be expected. I have the vertical intercept of my parabola, 0, 4. The second equation simplifies to a plus b plus c equals 28. And the third equation simplifies to 4a plus 2b plus c equals 20. Knowing that c is 4, I can substitute 4 in place of c in the second and third equations to simplify this a bit. So a plus b plus 4 equals 28. 4a plus 2b plus 4 equals 20. And moving those constants to the right-hand side of the equals sign, I have a plus b equals 28 minus 4, which is 24. And I have 4a plus 2b equals 20 minus 4, which is 16. So again, I have a system of 2 equations with 2 unknowns. A and b are unknown. So let's go ahead and solve this system. I think I'm going to use elimination on this system, and I think I'm going to eliminate the variable b. I'm going to do that by multiplying the first equation, both sides, by -2. So I'm going to multiply -2 times a plus b, and set that equal to -2 times 24. So that's -2a minus 2b equals -48. And my second equation, 4a plus 2b equals 16. Adding the respective sides together, I have 2a equals -32. Dividing both sides of the equation by 2, I have a equals -16. when a equals negative 16, using that first equation, we have negative 16 plus b equals 24. So b equals 24 plus 16, which is 40. And we already knew c was 4. So I've got a equals negative 16, b equals 40, and c equals 4. And I want to check that with the 3 solutions that I have. So using the variables that I defined, d equals negative 16 t squared plus 40t plus 4 would be the quadratic equation that I came up with. Now I want to make sure that the ball really was 4 feet in the air when it was kicked, 28 feet in the air 1 second later, and 20 feet in the air 2 seconds later. So for my check, if t equals 0, then d equals negative 16 times 0 squared plus 40 times 0 plus 4, which indeed is 4. So that checks. What about if t equals 1? Then d is going to be negative 16 times 1 squared plus 40 times 1 plus 4. That's negative 16 plus 40 plus 4, which is 28. So that solution checks. What if t equals 2? Well, then I'm hoping d is 20. Let's see what d is. d is negative 16 times 2 squared plus 40 times 2 plus 4. That's negative 16 times 4, which is negative 64, plus 40 times 2 is 80, plus 4. That's negative 64 plus 84, which is 20. So that checks. So let's go ahead and write our conclusion here. The quadratic equation that I found to model this situation of the ball being kicked in the air is d equals negative 16 t squared plus 40t plus 4. What's the maximum height of the ball? Notice the 3 points that we knew about are on this graph. This is a graph of d equals negative 16t squared plus 40t plus 4, the quadratic equation I just found. In looking for the maximum height, I'm interested in the vertex. Looking at the graph, I can't really tell exactly what the vertex is. It looks like it's pretty close to 30, but not exactly at 30. But I can use algebra to find this. I have a formula for finding the vertex. So here's my quadratic model. And I know that the t-coordinate of the vertex is going to be the opposite of b over 2a. In this case, that's the opposite of 40 over 2 times negative 16. That's 40 over 32, which is 8 goes into both of those, 5/4. Well, that tells me the time when the ball reaches the maximum height. I'm interested in what that maximum height is. So what I need to do is find out what d is when t is 5/4. So if t is 5/4, then d is negative 16 times the square of 5/4 plus 40 times 5/4 plus 4. That's negative 16 times 25/16 plus 4 goes into 40 10 times. 10 times 5 is 50 plus 4. 16 goes into negative 16 negative 1 times. Negative 1 times 25 is negative 25. So I have negative 25 plus 50 plus 4, which is 25 plus 4, which is 29. Remember when we looked at the graph, we said that it looked like the d-coordinate of that vertex was close to 29. So our graph does verify what we found. The ball reaches a maximum height of 29 feet. So now I'm going to turn this over to Steve, who's going to graph some more quadratic equations.